12 Thermal Fluid Systems WPR3 review session. Please take a moment and complete the time survey before moving on. We have two objectives: review the course content from the third block of the course and to talk about some problem solving procedures that will be helpful as you get yourself ready for the exam. So in the course, we are wrapping up, and if you're in the current semester of AY21-2, this syllabus will look familiar. This is the review session. There's a homework that's due today, and you must self-grade it tonight by 2200, as you can see here on the right-hand side. The WPR is tomorrow on the study day. We're at 200 points, 10% of the course grade. The content, chapter 18 and 19, and then you have the multi-sample experimental uncertainty section there in chapter 15 as well. Those are the sections of the text you need to read, and you're encouraged to go through and review those sections. Let's first begin with the Brayton cycle. The Brayton cycle is an ideal cycle, which means it's composed of 4 ideal processes. And in the first, you should be very familiar with the idealization of an isentropic compressor. Recall, isentropic means adiabatic and reversible. The next idealization is the combustor is a constant pressure device. Isobaric is the Greek term that refers to constant pressure, and so we assume that the pressure at state 2 is equal to the pressure at state 3. The next idealization is the turbine is, like the compressor, also isentropic, so it's adiabatic and reversible. You see there the net power produced by the system, the Brayton cycle system, is a combination of the compressor work, which should be a negative term, and the turbine work, which should be a positive term. The heat exchanger is the fourth and fictitious cycle component. Why is it fictitious? Because normally gas turbine cycles exhaust to the atmosphere, but we model that, the atmosphere being here, and we recover our initial condition through the atmospheric heat exchange, fictitious activity there as a constant pressure event. So the bottom line, there's only 2 pressures in the process. There's the low pressure and the high pressure side. There are compressor work as an input, heat transfer as an input happen in the first 2 cycle devices. There's work extracted from the turbine. The network is a combination of the compressor and turbine work, and the heat exhaust or heat rejected is to the atmosphere. On the right-hand side, you see the classic heat cycle diagram, and of course you have your high temperature source, which is modeled as a temperature in the combustor, and you have your low temperature reservoir as the atmospheric location of heat rejection, and so that's your low temp reservoir down here. So heat in through the combustor, heat rejection through the atmosphere. And this is a review. Recall, it's an idealization of the cycle: isentropic, isobaric, adiabatic, etc., being those idealizations. Diagrammatically, and this is something you should be familiar with, the Brayton cycle can be reflected on a PV diagram or a TS diagram, as in figure 18.3. So again, 1 to 2 is an isentropic compressor. That's work into the system from state 1 to 2S. That S is a very helpful reminder that you should be using some sort of isentropic relationships as you assess the cycle 1 to 2. And so 2S is your way to kind of remember, oh yeah, I should be using isentropic relationships either for variable specific heats, or if it's simplified and specified that you can do that, then you can look at constant specific heats as well. MC312 reference data card has a section dedicated to isentropic relations, both for constant specific heats and variable specific heats as well. 2 to 3, this is your heat input from the combustor. So we burn usually a fossil fuel of some sort, and that's your heat transfer into the system. 3 to 4 S, again, isentropic explicitly there. This is your turbine process there. And of course, that 4S is your reminder that you should be using some form of an isentropic relation as you look at the expansion across the turbine. And finally, that constant pressure heat rejection from 4S to 1. And that's Q dot rejected or out of the system. Of course, how do you know it's going to be out of the system? It will give you a negative value as you calculate Q 4S to 1. And again, on the TS diagram, those isentropic processes occur as straight lines, 1 to 2S here in the compressor and 3 to 4S here in the turbine. Simplification that might help you at some point on this is the net heat transfer is equal to the net power, and that's the heat transfer rate and the rate of which work is accomplished overall, the net, the combination of the compressor and the turbine work. Also recall that your net work term, this is a rate basis, is going to be related to the PDV. So this is with respect to time. So this is technically just a work term here. So we'll get rid of that little dot there and make sure that we just say that the work is reflected as moving boundary work, integral of PDV. So moving along, some problem-solving strategies for the Brayton cycle. Well, first and foremost, you need to know what kind of analysis you're going to do on it. Oftentimes, we use the cold air standard assumptions, CASA for short, which allows some simplifications in terms of you don't need all the tables in your reference manual in order to solve. So CASA stands for cold air standard assumptions. The biggest one we're going to focus on is cold specific heat constant. So cold and constant specific heats. Also important is we're going to treat the air, actually the working fluid throughout the cycle, as air and ideal gas. So we're not going to incorporate combustion products. Again, look at RDC, but you'll see some isentropic relations, much in the vein of relationships that look like combinations of temperature ratios, in this case, specific volume ratio, raised to powers that have the specific heat ratio involved. Also worth noting is the thermal efficiency of the cycle is going to be the net power produced, W dot net, divided by the heat transfer into the system. That's what I get out from my system based on what I get in. Lastly, and we haven't talked about this a whole lot, but it's probably important to recall, that the back work ratio is the ratio of the compressor power to the turbine power and we're going to put a negative sign there because we know that the compressor power term is indeed going to be a negative value, and to get a back work ratio that logically would be positive as a result. What you want to do is minimize your back work ratio for the power term, and you want to maximize your back work ratio for the propulsion side. So your back work ratio is going to be on the order of 1, or going to be equal to 1. Okay, let's move along to actual gas turbine engines, where you see a couple of important differences. So in an actual gas turbine engine, here's a line for P2 and here's a line for P3, and they're not the same pressure lines. In fact, what we're going to say is that P2 is going to be higher than P3. Why? We'll have a loss as we go through the combustor. A pressure drop is natural as you run your compressed ideal gas through a cycle component, in this case the combustor. So that's one of the examples, and of course you'll see a difference in pressure between 4 and 1 as well, and obviously we're going to incorporate pressure drop as that sort of so P4 will be higher than P1. Similar inefficiencies or actual cycles won't have isentropic components here. You can see this this change in entropy that's going to occur here between, let's see, this is the TS diagram. So we have that is delta S 1, 2, S. So that's the difference in entropy between the ideal and the actual cycle process. And of course, how do you handle that? Now we're looking at the isentropic efficiency of the compressor. And much the same way, we have this process here across the turbine. This would be the isentropic turbine, the idealization. This is the actual turbine. Not only will there be a different work output, but there'll be a change in entropy between the two. And again, isentropic efficiencies for turbines is where you would go and conduct some assessment between the difference between the ideal case and the actual case. Let's move along to how we're going to improve the performance of gas turbine engines. And the key here is the use of the device in that question mark up there. Yes, the answer is regenerator, and that is our primary means, our most important means to improve gas turbine performance. How do you do it? Well, let's see. We're taking this exit air from the compressor here, running it through a heat exchanger. That's the regenerator right here. This is our regen. And we're trying to get X high. Now, we want to get an increase in TX, and how are we going to do it? We're going to use that free exhaust that's sitting out there in this exit line. That's state 4, using the exhaust, which is T4. Obviously, there's an effectiveness associated with that, and you should look at that in your text. In fact, I would encourage you to write down the regenerator effectiveness equation, which talks about how much of the energy in line 4Y you're able to get into state X. And the hint here is you want state X to be as close to state Y as you can. Let's talk about some additional improvements beyond the regenerator. So the regenerator is your primary gas turbine improvements. You can make a regenerator perhaps work a bit better, albeit at greater cost and some maintenance related issues, by adding a couple more potential devices as seen in figure 18.7. The first is an intercooler, which allows you to get that increase in pressure that you desire without also dealing with the fact that the density of the gas is increasing as well. And so you intercool, cool the gas, allow for that pressure rise to happen with a lower density fluid. And that has an overall reduction in W.12 as the outcome from adding the intercooler. We've talked about the regenerator, increasing the temperature so you don't have to burn as much fuel to get from X to 3. So Q.X3 would be less than what Q.23 would have been in a standard cycle. You're going to add some reheat, either by burning some additional fuel or some other means, between turbine stages, increase the enthalpy of the inlet gas to the second stage turbine, and of course that'll get you more power out. So this is the reheat, and of course you're adding more fuel, you're increasing your temperature, but we know from our heat cycle analysis that that's an improvement in the net total power output. So the enthalpy, I'll say, is increasing at state D. Now, what is the impact on the thermal efficiency? So we're adding more heat transfer in, right? If you add a reheater, for example, over here, this is another one of these terms in addition to this term. So it's indeterminate from a practical sense of whether the thermal efficiency will increase, stay the same, or decrease. And how is it indeterminate? It depends on how much fuel you burn, what conditions you get, how the design is set up. So it can improve thermal efficiency, but doesn't necessarily have to. Another gas turbine cycle improvement is to combine a gas turbine, oftentimes in power production facilities, with a bottoming cycle, which is a standard steam cycle. Brayton and Rankine cycles together are combined cycle processes, and you remember Rankine cycle analysis from MC311. And of course, the Brayton cycle is what we're have here. An analogous term is a topping and bottoming cycle. And I'll refer you to your text because this portion of the analysis is essentially the same as a Brayton cycle analysis or an actual gas turbine cycle analysis when we count for isentropic efficiencies and pressure drops. Down here we have, of course, the standard Rankine cycle, which is a review of last semester and not one of the objectives of MC312 per se. The next topic we covered, aircraft propulsion. We set it up by doing both the force and momentum diagrams, and so we leverage the force diagram and get the sum of the forces that are involved in our transactions here. Here we have pressure terms across areas in which they operate. Notice those arrows are inward and normal. And then you have the time rate of change of momentum, which we'll simplify as MA terms on the right-hand side. And of course, if you look at the summation of the forces, and you get the inlet pressure, inlet area, you subtract the exit pressure, the exit area, and you add that net force on the air term, you can calculate that the force due to thrust will be the mass flow rate of air through your engine times the difference in velocity between the exit and the inlet. Oftentimes that inlet velocity would be the aircraft speed. So the higher you can get this exit velocity, the more thrust you'll be able to get. So you should recognize this jet engine. And you know there's several types of jet engines. This one should come to you quickly as a turbojet. You can identify a turbojet quite quickly by noticing in this case, all the air goes through the engine. So it doesn't have any bypass. Turbofans have a bypass. Air goes through the engine as well as around the engine. And then you also see that there's a compressor and turbine linked and nothing else. There's no external shafts, and so another indicator of a turbojet engine is there's no shaft involved, unlike for example, a turboprop might have. So how do you analyze the turbojet cycle? Well, it's reasonably straightforward. There's some idealizations in this particular diagram. You can see here we have isentropic nozzle and diffusers at the front and back ends. The compressor and turbine can be isentropic. Again, every time you see those isentropic processes, you'll want to use the isentropic sections of your reference card. You have a constant pressure combustor as before, and again, if you had an actual turbojet engine, you would have some deviations and use isentropic efficiencies for compressor and turbine. Potentially have them for diffusers and nozzle, although those things have very high isentropic efficiencies. And you can see here we add in with the nozzle and the diffuser this section of the Brayton cycle diagram here where you have flow through the diffuser and flow through the nozzle respectively. So we have several more too, reversible and adiabatic processes by adding the nozzle and the diffuser. You're going to see an increase in the inlet pressure through the diffuser, and you're going to reduce the velocity of the air as it goes through that initial diffuser as well, which is obviously why you have the diffuser there. A little bit easier on the engine components. So some problem-solving strategies you can use with the turbojet include recognizing the linkage between the compressor and the turbine. The only thing the turbine powers is the compressor, and therefore their work terms must be equal and opposite. So W dot C, which is the compressor power in a negative term, would be equal and opposite to W dot turbine, and that's one of your key idealizations. Again, isentropic relations are used heavily, and you either use tables if you're using the air standard assumption, or isentropic relationships that involve the letter K. In a cold air standard analysis. What do you do to improve turbojet performance? Well, maybe you want to go faster. And so this is an example of a schematic where you have a device that follows the turbine. Here you're going to burn additional fuel. And so this is an example of a turbojet with afterburner. And what's going on here? We're going to add more heat transfer by burning additional fuel in the exhaust section of the turbojet. Doing some analysis with the afterburner, we basically add on this device right here. It's a constant pressure device is how we're going to treat it. We have a heat transfer in to the system, so obviously your thermal efficiency will have a larger denominator than it might otherwise have without the afterburner. You should be familiar with the common aircraft propulsion types. We have a turbojet. We've talked about that. When you see the bypass air going around the engine, that should alert you to the turbofan. And then finally, you can see the large propeller on the front, which is a dead giveaway for the turboprop. The next section, and the final section, that we talked about in this block 3, is compressible flow. Recall in compressible flow, we oftentimes use a moving reference frame here to develop the key equations about what happens in a pressure wave. And so we can look at small differences in pressure, density, and even velocity in this moving reference frame, moving control volume, to develop our basic equations. Speaking of pressure waves, we have some conditions here that are probably given away by these terms right here, but notice the pressure wave is symmetric about the source if there's no movement. There's some movement. In this case, the air could be moving in the x direction. An object could be moving relative to that. This is one where there's a subsonic type flow, so the velocity is less than the speed of sound at that condition. Here's one that reflects that the object is moving right at, your sound waves are right at the front of the object, and therefore it's moving at the speed of sound. This would be, for example, time equals 0, and we'd be at this position. If that dot there indicates the position of the object, that's t at some time interval prior to 0, so that would be negative delta. That should be a delta t. And this is, of course, the sonic condition there. And finally, when you have this behavior where you see a shock wave essentially ahead of the object, then now we have a supersonic type condition. And so the velocity of the object would be greater than the speed of sound. The reference data card, of course, I've been talking about this throughout, these isentropic relations here for constant specific heats. And of course, you would use these with the tables. Those are table 8 or 8 echo, would be appropriate to use for variable specific heats. I'd also like to point out how lean the section on compressible flow is. There's not much here, folks. And so this is a great area to focus on writing down some of those key equations that develop table 18 and even table 19. The tables are very useful for actually doing the calculations, but the relationships may also help you to have ready at your disposal for the exam. Related to those are the area and velocity relationships between the different kinds of nozzles and diffusers. And of course, to know a nozzle versus a diffuser, you got to know the flow regime in which it operates. This first one here is the one we've been most familiar with in the course up until the compressible flow section, and that is a standard subsonic nozzle, which has an area contraction. Now, nozzles by definition always increase flow velocity. Nozzle increases velocity, and so in the subsonic condition, it's a contraction. Diffusers always slow the velocity of the flow. So that's the difference, and they look different based on the regime. So obviously this is the diffuser here, but when we get to the supersonic case, and that 1 minus Mach number squared term kicks in to become a negative value, the supersonic nozzle then becomes an area expansion, whereas a supersonic diffuser becomes a contraction. And there's a relationship there that you should have handy and with you. Now this schematic, this figure, 19.5 here, talks about 4 different cases based on the back pressure, and you should be able to navigate this reasonably quickly and understand that there's no flow case if your back pressure and your stagnation pressure are the same. These are pressure-driven flows, and without a pressure differential, there won't be flow. The first case is sort of your standard subsonic case. Could be slow flow, or it could be just subsonic flow. And the back pressure is lower than the stagnation pressure, but not so low as to cause any sort of shock or choking condition. If your back pressure here in case 3 is equal to your critical pressure, then you can get to the Mach equal 1 condition at the exit. Just beyond the exit, this business here discusses what happens if the pressure beyond the exit is below that critical pressure, in which case then you'll have a shock wave develop. You won't have flow in the nozzle that gets faster than Mach 1 if it's shaped like this, because it's a choked flow. The converging diverging nozzle is actually how you get flow to exceed Mach number 1 in an internal flow. And we model this flow as isentropic. So there's no shocks in this diagram that we have here. So we'll model the entire flow as isentropic. We have an inlet that's got a Mach that's less than 1. We achieve a critical condition at the float where the Mach number is 1 at the throat, and at the exit we're allowed then to have a Mach number that's greater than 1. The several cases here on the bottom indicate where shocks may occur, and so that's what these squiggly lines here, they're all shocks. They're all based off conditions of the exit or back pressure. Briefly on shock waves, there's basically two types. Here we have an oblique shock wave. Down here is an oblique shock wave. Oblique shock waves are not covered in the text, and they're any shock wave that's not perpendicular to the object. And so right here in this section, we would approximate this section as a normal shock, perpendicular, and so therefore at the front of our object, we would call that a normal shock. I would encourage a look at example 19.4 as you look at your converging, diverging nozzle with a shock wave. And of course, the key here is we're isentropic up until point A right here, and isentropic from B to the exit, but we are not isentropic across A to B. And so you can look at that example for some help on how you do shock wave related problems. Okay, you know that this section of the course was focused on chapter 18 and 19 primarily. There was one section in chapter 15 dealing with multi-sample uncertainty that might be worth a quick review. Recommend you focus on the lesson objectives, and I think I've summarized the vast majority of them in this. And then you got to know what's on your RDC, and what isn't on your RDC needs to go on your one-page sheet that you bring to your exam. The reference tables can't be discovery learning during the exam, especially for the compressible flow. Check out table 18, and if necessary, table 19 as well. Those give you Mach number relationships through the specific heat with ratios of temperatures, ratios of pressures, ratios of densities, and in critical conditions, ratios of areas. Write out the important equations. And what I'm not going to show you are any example problems now. You need to practice your 3 throws and then go check example problem solutions. This concludes your WPR review. Good luck.